Okay, this presentation is on geophysics for porphyry copper deposits in southwest North America. This has been based on career observations at numerous deposits that Freeport controls and is mining, some other exploration projects, and it is essentially just a summary review of what seems to work and what doesn't seem to work. And it is an integral part, geophysical integral part, has been and continues to be an integral part of exploration for porphyry copper deposits. As most currently producing porphyry copper deposits in southwest North America were partially outcropping, geophysics was often used after the fact. Discoveries of the Mission deposit and the larger resource at Lakeshore were greatly assisted by geophysics, magnetics in the case of Mission, and IP in the case of Lakeshore. Case histories in in-house geophysics for the last 50 to 60 years provide a good template for continuing exploration. With outcropping targets largely a thing of the past, geophysics has a much larger role in exploration. Magnetics and IP are still the most useful in porphyry copper deposit exploration. As such, these methods, particularly IP, are the focus of this presentation. Large dipole IP, 300-meter dipoles or greater, is critical to get depth of investigation for buried targets. Alternative IP arrays such as RIP or vector IP can provide aerial coverage for buried targets. EM techniques such as MT and ZTEM are passive and deep sensing and can also be used for deep targets. Starting off, what are the characteristics, geophysical characteristics of the porphyry copper model? Using USGS modified Lowell and Gilbert porphyry copper model, which combines both mineralization and alteration, you can see that there's different responses, geophysical responses, that are associated with the different alteration types primarily, but to a lesser degree, the mineralization. And overall, you see that magnetics, when you're out in the propylitic zone of a porphyry, can be high to transitional. As you get into a xercitic zone or a phyllic alteration zone, which is magnetite in structure, you have a mag low. Once you get into the center of the system, the potassic center of the system, where the primary mineralization is concentrated, you will have a mag high because magnetite is stable. And you may have, in addition to magnetite present in the causative intrusion, you probably have early magnetite veining associated with secondary biotite chalcopyrite. So, and also if you have a skarn peripheral to the porphyry, you'll expect mag high. And the other thing with a skarn, you may have a gravity high. So when we go and look at more the mineralization and the pyrite content, what you see in the low pyrite shell generally is resistivity is variable, can be fairly low if there's a lot of fracturing. IP response is maybe 20 to 25 milliradians, milliseconds, millivolts, however you want to consider it. The pyritic shell, though, where you have pyrite in excess of 10% and much greater than chalcopyrite, you should expect the IP response to be well over 50 milliradians, sometimes in values much higher than that. And within the ore shell itself, where your ratio of pyrite to chalcopyrite is, let's say, 5 to 1 down to 1 to 1, you should see a lower IP response 25 to 30 milliradian, and the resistivity is generally much higher than what you see in the pyritic shell. Example of using magnetics for porphyry copper exploration is looking at the regional trend coming all the way from Mexico on the south end, La Caridad, which is a major porphyry copper, going through Cananea, which is a world-class porphyry copper deposit, with various smaller deposits in the vicinity of Cananea, coming up through Red Mountain, which is unexploited porphyry copper with oxidized capping, and all the way up to Sierra Esperanza, which is a mine of Freeport's currently being mined, Pima-Mission, which is mined by Ozarko. And you can see on these trends that the structural trend of this northwest arrangement of these porphyry copper deposits, which is essentially a basin and range trend, but it is exploiting older trends and probably an arc parallel trend at the time of formation of these porphyry coppers. In certain of the porphyry coppers, particularly La Caridad and to a certain extent Cananea, what you see is mag lows, which have to do with extensive magnetite destruction from phyllic alteration. You don't see a similar type thing happening at Sierra Esperanza. That's because you don't have a lot of phyllic alteration there. It is primary mineralization, which is low grade but widespread without a lot of strong phyllic alteration superimposed. Example of a porphyry copper with a skarn deposit is from our New Mexico mine at Chino, or Santa Rita deposit, with the northern part of the district being the Pobres deposit. There are skarns developed the Pobres deposit. Essentially, it's all skarn mineralization, over 1% copper, and the skarns around the porphyry at Santa Rita have been mined for very good grades of copper. You can see that strong skarn response is overwhelming the porphyry response, which is a small lower value in the center. Silver Bell area, there's a regional total magnetic intensity. You can see that is highlighting some major regional faults that control positioning of deposits, and both the North Silver Bell and the El Tiro and the oxide pits all occur within overall lows. And at North Silver Bell, where we did a complex case history, when you look closer in with ground magnetics, you can see that the stock, which is potassically altered, has a higher magnetic response, reflecting primary magnetite mineralization that hasn't been overprinted by sericitic or magnetite destructive alteration, such as you see in the phyllic zone. And then once again, back out in the porphyritic zone, you see high mag response again. Next, I'm going to talk about IP with porphyry copper exploration and the dependence of depth penetration on the size of separation between your transmitter and your receiver, which is affected by having larger dipoles. You get more separation, deeper penetration. First example I have of a Ford model is a potassic core which has a 25 milliradian response, 150 ohm meter resistivity. The Philips zone, I've given it 60 milliradian response with a lower resistivity, 30 ohm meters. Propylitic, I have still some IP response, 15 milliradian, but higher resistivities, 200 ohm meters. And then the background is 200 ohm meters with 5 milliradian response. So as you can see, if you run it's exposed to the surface and you run a survey, you nail exact placement of where the deposit is, very strong IP response with much higher kind of on the edges of it, reflecting that Philips zone response with a lot of pyrite. But it doesn't dramatically show up in the resistivity. You do have lower resistivities associated with that Philips type response. Next model is for putting 300 meters of gravel over the same model. And again, you can determine in the IP response, there's a nice response still, even with that 300 meters of gravel covering. You're still seeing a background, of less than 5 milliradians with values going up into the high 20s associated with the Philips alteration. But in the resistivity, there's essentially no good discrimination. What's there is very subtle. And to take this model further, what I've done is bury it at put 600 meters of gravel over the porphyry copper. And as you can see, still in the IP response, you're getting a good response. It's more muted than what we saw before, but still 3 times or more what background response is. So for a comparison between, choosing a dipole length of that separation between the transmitter and the receiver is critical to seeing through conductive cover. And what I've done is I've simplified the porphyry model. I don't have the same exact model I was using in 3 previous examples. But here we have the porphyry has 100 ohm meter with 30 milliradian response and a background of host rocks with 300 ohm meter with 10 milliradian response, and with the gravels essentially having 20 ohm meters and 5 milliradian response. And you bury it with this, you still, in the IP, definitely get the 2, not quite 3 times background, but 2.5 times background response at depth for where the porphyry is. It's indiscernible in the resistivity response. Now, the same model is applied to using dipoles of only 100 meter separation. And the point is that here it's very difficult to see, even in the IP response, any significant difference between background and where the porphyry is. There's a very subtle, but it's less than a 20-25% difference. So next I'm moving on to an area where we have extensive IP collected more than 40 years ago, actually more than 50 years ago, but which was of good quality and which we had input and modeled to show examples of the IP response over the very giant Lone Star response, Lone Star deposit, the Dos Pobres deposit. As you can see on the Lone Star modeled response, the IP where the oxide, there is deep oxidation down to as much as 3,000 feet of oxidation. And as you can see, there is really no IP response associated with that. On the flanks, though, there is still high IP because there's sulfides, pyrite as well as copper sulfides on the flanks of the deeply oxidized area. And with the resistivity, you see similar sort of relations. You see, instead of low resistivity, you see a slightly higher resistivity associated with where the copper oxides are, where the sulfides are, is lower resistivity. Another example from the district is the Dos Pobres, and essentially the IP models exactly where the Dos Pobres deposit is. The Dos Pobres deposit is unique in the district in that it has quite a bit of bornite associated with it as well as gold. And it has been offset by the Butte Fault. And that shows up both in the IP model we did and in the resistivity model. You can see that offset really well in the resistivity model and almost gauge what the offset is, which is about 1,200 feet or so. Another thing that we consider in exploration, if we have a lot of ground to cover and we have a buried target, is how do we cover that ground effectively? And one way to do it is using reconnaissance IP. Some people call it vector IP, which essentially consists of putting out a large dipole of 5,000 feet or so, and then making measurements of two orthogonally oriented dipoles. And the dipoles, the vector difference in the responses from the two dipoles gives you the response for that position. And as you can see where the Dos Pobres deposit is, we got responses that are commensurate with what you would see with the dipole line, which was run over top of the same area. You're seeing responses in the RIP survey of as much as 60 milliradians, and that's similar to what we're seeing in the dipole. Another example of the RIP was at the North Silver Bell deposit, and the outline of the deposit shows almost exact coincidence where the highest IP response was determined from a transmitter located up to the north and about 3.5, 4 kilometers distant. Another example from the North Silver Bell study is the use of resistivity in determining where you are in the alteration of a porphyry copper system. As you can see, strong phyllic alteration, which is adjacent to where the main resource chalcocite enrichment zone is very low resistivity compared to over to the Potassic alteration zone where resistivity is increased and the propylitic zone. Here's an example of how other techniques can be used in exploring for porphyry coppers. It's from a ZTEM survey that was flown over the Lone Star deposit. The data were inverted and processed, and you can see the break in essentially more conductive material is where the Lone Star deposit is showing up. And what we saw previously from the IP survey is the resistivities are higher compared to the neighboring rock because of the oxidation. And that's being shown very beautifully by this example. And next, I will talk about the use of Spectral IP for discriminating sulfides and different ore types. This is an area that has essentially not seen much development since the 70s, early 80s. And we conducted a survey using this technique at the Garfield deposit, which is in our Morenci mine area. The Garfield deposit is a large, over 2 billion tons at plus 0.3%, and consists of various ore types, oxide, enrichment, as well as primary ore. And to make the argument for discrimination of sulfides by looking at different frequencies, which Ken Zonge did and Bill Pelton both did in the 70s, which the frequencies are related to the time constant. And if you can see, the same diagram gives the argument to both sides that increasing grain size, essentially you get an increased time constant, whereas looking at the same figure but highlighting where copper versus pyrite is, you see that there's also separation, that you get a larger time constant with pyrite. This is an example of varying grain size along with the different species. And from these tests that were conducted in the laboratory, using different grain sizes and making artificial rocks with these grain sizes, you can see that, yeah, there's a separation in the frequency of maximum response depending on grain size, but there's a separation between chalcopyrite responds at higher frequencies than does pyrite. And if you look at the lowest frequency, generally pyrite peaking about 1 hertz, whereas chalcopyrite is up around 7 to 10 hertz. So the case history involved running a series of lines over the Garfield deposit, which is a mix of oxides and enrichment. I highlighted a few lines in red. I'm not going to show all the lines. I'll show 2 of the lines, starting with, before we go that way, talk about what the spectral types, which were defined by Ken Zonge. They're essentially looking at the slopes. If you plot the real versus the imaginary response, which is essentially a function of the vector, mag, and the phase. So if A slope is greater than 20%, then you have intermediates. B is essentially a flat slope. C is a strong slope in the other direction from A. And then the ore types that we're looking at are listed there. And the conclusions from looking at all the lines was we had specific spectral responses associated with different types of mineralization. The chalcocite being really highlighted more by a B-type response, primary being variable from a B to a more A response with more pyrite. So the first line we're looking at is line 1 east. You can see the different ore types put on section, and with the proposed pit, I'm not sure where that pit is these days. And you could see there was a fairly strong IP response at depth, with indicating primary mineralization beneath all these other ore types. It's in excess of 30 milliradians. You can see resistivities for the same section, and the resistivities tend to be, they're higher underneath the leach capping, which is kind of contrary to what I've seen in some other systems. And again, here we have the ore types, and now we have the spectral types. What these two letters are, the first, essentially you're going from 0.125 hertz up to 10 hertz. We're not looking at the highest part of the spectrum. And as you can see, discrimination, chalcocite seems to be favored with the B-type response in general, but it's difficult to put the spectral section, because it's not modeled, to fit exactly how it fits. And by modeling the spectral section, probably would see a better coincidence with ore types. Now we're going to look at another section, which was line 5 east. It has a consistent enrichment blanket across it. You can see there's essentially very little IP response in the covering leach capping, and it starts increasing in response about where the enrichment blanket is. It goes to the highest values beneath enrichment as you get into primary. And the resistivity again, lower resistivities up in the leach capping or oxidized material. And you're getting a change in resistivity right at the interface between the oxide, leach capping, and the enrichment. And here, the spectral type really works very well with this B-type response, characterizing the enrichment zone. It's in most places a strong B-type response, which means very flat response when we have capital B, capital B. So just gives you some idea of where we're at. 30 years ago with using spectral IP to discriminate between copper-bearing sulfides or mixes of copper-bearing sulfides with pyrite versus just pyrite. Thank you. Some of the conclusions are the resistivity data, the leach capping, oxide mineralization don't directly correlate with higher resistivity values. Resistivity is affected by a combination of lithologic changes and faults. 6 of the lines approximately parallel to the dominant northeast fault trend. Lower resistivities on the ends of the northeast lines correlate with the location of the Garfield fault. Generally, primary mineralization is characterized by high resistivity. Higher model IP values map either the contact with primary or with thicker chalcocite zones above primary. Lines with the highest IP response have primary mineralization closest to the surface. High IP values are modeled depth of only on lines 3 and 4, suggesting the center of primary mineralization is in this area. On the other lines, model high IP values are lenticular zones underlain by lower values, indicating a lack of primary sulfides at depth. standard IP response, high IP zones that project to the surface, such as the east end of line 8, correlate with known outcropping sulfides. The range of observed higher IP values, 25 to 40 millirating, by comparison to results in other disseminated sulfide systems, equates to only about 2 to 3 volume percent sulfides. And the spectral IP, which is based on 15 frequencies, after the response from those is decoupled, the field mesh is decoupled, the spectral data can be used to help discriminate the source of IP response, sulfides from clays and graphite, as the limit degree species of sulfides. And here are the responses we saw for the different zones. And laboratory measurements that we made of core samples from Garfield showed that the highest IP response has spectra varying from A to B dominant. In other words, from pyrite to mixed copper sulfides with pyrite. Samples of calcite have a definite B character. So, to enhance the utility of spectral data, there needs to be quicker acquisition, more density of data, and modeling of the spectra. All these have been developed in the last 10 years or so, but weren't applied to this particular case history. Thank you.